What we want to do in this problem is we want to try and solve it. So the first thing that I would do is I would write it in matrix form with the prime notation, which makes it a little bit easier to read, at least in my opinion. And then we'll have the coefficient matrix here, which is a 3, a -1, and a -1, a 1, a 1, and a -1, and a 1, -1, and a 1. I close this up, and I multiply it by x, by y, and by z. Okay, well, now that we have this, what do we do? Well, this is what we do. For a 3×3, to find the eigenvalues, I would put it in MATLAB, and I went ahead and did that. And I have the answers right here. So this is how I did it. I basically just used the eigen function, which gave me, and I put in the matrix, where this is the first row. So to tell MATLAB this is a matrix, you have to put the square brackets. And then the first row is separated by a semicolon, second row by another semicolon. And you do that, and it gives you the eigenvalues. And the eigenvalues, in this case, are 1, 2, and 2. So we see we have a repeated case of eigenvalues. We have lambda 1 is equal to 1, but lambda 2 is equal to lambda 3, which is equal to 2. So let's deal first with the easy case. We got our distinct eigenvalue, lambda 1. So what we do is we write, let's do it over here. So let me make some room. Right here, lambda 1 is equal to 1. So I'll write for lambda 1 equal to 1. For lambda 1 equal 1, what do we have? Well, we need to subtract that to all the diagonals. So that's 3 minus 1, which is 2. -1, -1, 1. 1 minus 1 is 0. -1 stays the same. 1 stays the same. -1 stays the same. 1 minus 1 is 0. Then we go ahead and write the, what do we write? We write the vector k1, and let's not call it k. What can we call it? I'll call it x. No, let's call it y. y1, y2, y3. And that's going to be equal to the 0 vector, because we're looking at the eigenvalue problem. So what we do now is I would augment it. I would not try to substitute back and solve it by hand. I would just augment the matrix, which is right the left matrix, the big 3×3, and then add whatever is here, because the relationship stays even without the name of the variables. And to signify that it's augmented, you can put a bar right here. And then you put it in MATLAB, and you RREF it, which means you do the reduced row echelon form. And I'll show you what it does. So if I do the reduced row echelon form of the matrix 2, -1, -1, 0, and 1, and 1, 0, -1, 0, and 1, -1, 0, 0, what I get is 1, 0, -1, 0, 0, 1, -1, 0, and a whole row of zeros. Okay, so now I can plug back in, just remembering the order of the variables. And if I do that, I'm going to get x plus 0y minus, sorry, I had y1, so y1 plus 0y2 minus y3 equals 0. y2 minus y3 equals 0. And we don't have y2 by itself. So let's say that y2 is equal to t. If y2 is equal to t, then y3 is equal to t as well. y3 is equal to t as well because I'm just saying y2 is equal to y3, but y2 is t, so y3 is also t. And if y3 is t, then y1 is, which is equal to y3, y1 is also t. So we can just say that our first vector y is equal to t. But let's just let t be 1 because we don't care about the length of the vector y, we just care about the direction. We have our first eigenvector. We can do a similar thing for the other two cases. And if you remember, we have them over here. They're both eigenvalues of 2. So for lambda 2 equals 2, I put that back into my matrix. So that was 3 minus 2, that's 1. Negative 1 and negative 1 stay the same. Then 1 minus 2, that's negative 1, and negative 1 stays the same. And 1, negative 1, and 1 minus 2, that's negative 1. Now we close this. And here, I'm going to have K1, K2, K3. And that's all going to be equal to 0, 0, 0. Once we have that, we can solve it by putting it in MATLAB after augmenting it once again here. And if you do reduced row echelon form, which you can do by hand, but it takes a little bit of time, if you put in MATLAB, it'll be quicker. Once we do reduced row echelon form for this case, we get 1 minus 1 minus 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. That's interesting. Well, we have two rows of 0. So when we plug back our values, we get K1 minus K2 minus K3 equal to 0. We get to choose two values. So let's choose K2 equals a T and K3 equal to S. Then K1 is equal to T plus S. So let's say let T be equal to 1 and S be equal to 0. Then what are we going to have? Or T be equal to 1 and S be equal to 1. Then we're going to have our K vector is going to be, well, what is K1? Well, that is T plus S. And if T is 1 and S is 1, then K1 is 2. What is K2? Well, we said that T is 1 and K2 is T, so that's 1. And K3 was S, which is also 1. So here we find another vector. But are we able to find another linearly independent vector in this situation? Well, I think we can, because if we let K2 be 1, if we let T be 1, and S be 0, then we're going to find another vector, call this vector P, where the top one is going to be K1, which is T plus S, which we said is 1 plus 0, which is 1. The middle one is going to be K2, which we said is T, which is 1. and the third one is going to be 0. So then we have these three vectors, and they're linearly independent because there's no way I can multiply this by a scalar, like 2, and get this, right? Because there's that 0. And to get that 0, I'd have to multiply the top by 0. But that would make everything else 0. So I know that these are linearly independent. And if you are uncertain, I would suggest to put it in the Vronskin, in the matrix version of the Vronskin, and see if it equals 0. And if it doesn't, then you know that they're linearly independent. So then we can say that the general solution for this is going to be x. Well, because for each vector, we can find the solution, a particular solution. In this case, it would be 1, 1, 1, e to the, what lambda was this for lambda equal 1, so the 1 times t. And now for here, we'd have x2 is equal to 2, 1, 1, and this was for lambda equals 2, so e to the 2t. And here we have x sub 3, and we have 1, 1, 0, e to the 2t, because these have the same lambdas. So now if we add these together by creating a linear combination with constants, we get c1, 1, 1, 1, e to the t plus c2, 1, 1, 0, e to the 2t plus c3, 2, 1, 1, e to the 2t. And this should be our answer. Okay, so this was another case with repeated roots, but in this, yes, with repeated eigenvalues, but in this case, we had a way to find independent eigenvalues without resulting to the other method of having to multiply by t and then solving for that other system for the p vector and so on. I hope this was useful to you. It definitely was to me, and I will see you next time.